In this video, we're going to solve a typical static equilibrium problem for a beam. What we're given here is a beam hanging off a boom. It's hinged at the wall. There's a cable also supporting it horizontally, and then you have this safe hanging from the end of the beam by a rope. So we're given some helpful information here. The safe has a mass of 430 grams. You're given the dimensions of the boom, the mass of the beam, told that the mass of this cable is negligible. We want to find out what is the tension in this cable and what is the force exerted by the hinge on the beam. All right. Let's just write down some of our information right on the diagram because that will be helpful. Our safe is 430 kilograms. That includes the mass of the cat. The beam, 85 kilograms. A is 1.9 meters. B is 2.5 meters. All right. So we're going to draw a force diagram for the beam, all the forces acting on the beam. Let's start with the force of gravity on the beam itself. It's assumed to be uniform in composition, and we can treat that 85 kilograms then as it's acting all in the center of the beam. So let's draw an arrow for that, and right in the middle there, then we've got force of gravity on the beam. We also have a rope hanging down. That force from that rope is quite a bit more because the safe is so heavy. We have a horizontal force here from the cable. And then we have the force of the hinge. Now, hinge force, it'll be different from a normal force. A normal force would only act perpendicular to the surface, but because of the way a hinge is composed, the force can act in any direction. We don't know the direction, so we'll set that up with components, an x component and a y component. And we don't know that the x component is to the right or the y component is up, but we will just draw them that way, and then if it turns out they're the other direction, it'll come out in the math and we will know. So let's just label those. There's the force of the hinge in the x direction, the force of the hinge in the y direction, the force of gravity on the beam, force of gravity, no, we're not calling it that. That's going to be the force of tension in the rope and the force of tension in the cable. So we're going to be trying to solve for the two components of the force from the hinge and the force of tension in the horizontal cable. We can calculate the force of gravity from the beam and the safe, and I won't go through the details of those now, but I will tell you the results. From the safe and the cat, 4218 newtons. No. And from the beam, 834 newtons. Okay, we're solving a static equilibrium question for an object where forces are acting in different locations. We have to consider more than just that the forces all add up to zero. We have to consider torques as well. So this will be the new step beyond what you already know how to do. Static equilibrium, summation of forces is 0, and summation of torques is 0. Let's deal with forces first. That's what you're familiar with. So the sum of the x forces. We have the force of the hinge going to the right, and to the left, force of tension in the cable. And I think we're stalled at that point. We don't know either of those. So we'll be back here, but let's move on in the meanwhile. Now the y forces also have to be 0. So upward, you've got the y component of the hinge force. Downwards, you've got the force of gravity from the beam and the force of tension in the rope. And this we can solve. So the hinge force is going to be 834 newtons plus 4,218 newtons, the y component of the hinge force. Equals 5,052 newtons. All right, so that's as far as we can get for the forces. Now let's consider the torques. In equilibrium, all the clockwise torques have to balance all the counterclockwise torques. So the first thing to do is to choose the point that you're going to calculate the torques through. I highly recommend in this case that you calculate all the torques around the hinge, because we've got an unknown force here through the hinge. It won't come into the torque calculation. This looks like it will allow us to find the force of tension in the cable because we know the other two forces. So let's start to do this. We'll start with the counterclockwise torque, the torque from the cable. So you know how to calculate torques. You're going to do R, the distance from your pivot point to where the force acts, times the magnitude of the force, times the sine of this angle theta. But I'm actually going to calculate it another way. There's another equivalent way to calculate a torque. Sometimes the one I just described is easier. If you know this length and you know theta, just go ahead and do it. But we don't in this case. And I want to demonstrate this with a little proof. And we'll just do this off to the side. Okay, this is your pivot point. That's your beam. And this is your force. This is R. This is theta. Now let's just complete that as a right-angled triangle, and I'm going to call this distance L. So the torque, as we know, is RF sine theta. But sine theta is opposite over hypotenuse, which is L over R. So canceling the R's, the torque is equal to F times L. So that is, if you continue along the direction of the force and you drop a perpendicular to it from the pivot point, you can just calculate the length of that perpendicular times the magnitude of the force. And that's what I want to do in this case, because we're given the length of that perpendicular is 1.9 meters. All right. So let's just expand this first. Summation RF sine theta equals 0. And we said for that first torque 1.9 meters times the tension in the cable. Okay, so 1.9 meters times the tension in the cable. Now for our clockwise torques, let's do the tension in the rope from the hanging safe first. So we know the force, and we'll do the same thing. We imagine the line of the force extended and dropping a perpendicular to it from the pivot point. That is the same as the 2.5 meter dimension that was given. That's why it's easier to do it that way, because we're given those dimensions. So we have 2.5 meters times 4218 newtons. Okay, and for the third force, the third torque from the force of gravity on the beam, all right, so that's exactly halfway along the beam, so this distance will be 1.25 meters. And that's 834 newtons. And so that allows us to solve for the tension in the cable, which is about 6,100 newtons. Now going back to this, I see I've changed my notation for the tension. Then your X component of the hinge force is also going to be equal to 6,100 newtons. Okay, so we're doing well. We've got our tension. We have the two components of the hinge force. So to find out the overall force of the hinge, we're just going to need to turn that back into a single vector. So that way we have 6,100 newtons. That's our Fx. This way 52 newtons. And so when we add them together, this will be the force of the hinge. X component (6,100 newtons), Y component 52 newtons. So we'll apply Pythagorean theorem and use the tan of that angle theta, and we'll find that the force of the hinge is 7919 newtons, 39.6 degrees above horizontal. So then just to sum up then, we were to find the tension in the cable and the force of the hinge. It looks like we should report in 2 significant digits. So let's just do that in our final statement. Therefore, the tension in the cable is 7.9 times 10 to the 3 newtons, 40 degrees above. Well, that is not right. The force in the hinge, there we go. And the tension is 6.1 times 10 to the 3 newtons. Okay, so to review, gather all our information, draw the body that you're analyzing forces on, draw all the forces. The conditions for static equilibrium, the forces and the torques have to balance. So deal with the X and Y components of the forces, deal with the torques, start solving, and there you go. Now, you go try one.